In this experiment, the main objective is to determine the settings of a numerical overcurrent relay and to conduct the fault testing using a distribution line prototype available in this kit. Overcurrent relays are often used in distribution line, and when the current is greater than the pickup current of the relay, it tripped after the predetermined time based on the equation, that is IEEE or IEC CARA, whichever the relay follows. And in this experiment, the results will be verified by comparing the observed relay characteristics and tripping time with the expected performance based on the relay specifications. The circuit diagram shown here is the same as that of the numerical overcurrent relay kit, which consists of 4 impedance Z1 to Z4, and also the breaker R1 breaker. It is a solid state relay. And in this exercise, here a given distribution line of length AB, section AB, which is protected by this breaker R1, and this breaker is to be controlled by this numerical overcurrent relay kit. What we want to determine the relay settings to satisfy the following condition and also to be verified the result experimentally. The conditions are a fault occurring at F3, the relay to tripped within 3 seconds, and also if there is a fault is occurred at F2, the relay to trip instantaneously without any delay. And the relay used the IEEE moderate inverse curve as the characteristics for settings calculation. The data required for this test is tabulated here. Here we want to create fault at F2, F3 and also F5 for determine the relay settings. The corresponding current are IF2, IF3 and IF5. Why this current is required is that the IF2 current is required because in the question itself it is mentioned that the relay to trip instantaneously when there is a fault is occur at F2. Why we want IF3 is, in the question one of the condition is that the relay to be tripped within 3 seconds if there is a fault is occurred at F3 point. And F5 current, IF5 current is needed for setting the pickup current of this relay. The pickup current I pick of the relay is determined based on the minimum fault current and the maximum load current. If the pickup current is less than the maximum load current, the relay will trip even when there is a high load current. And also the pickup current should not be greater than the minimum fault current because the relay will not be sense the fault occur at F5 points. Therefore, the current IF5 is also very important to determine the pickup current of the relay. Next, we do the experiment in the given kit and create fault at various points like F2, F3 and F5. Thereafter, based on this current, the setting of the relay is to be determined to satisfy the above condition. Upon launching the software, 3 core modules are available to explore: fault current determination, numerical overcurrent relay experiment, and relay coordination experiment. Begin by clicking on the fault current determination module to find the fault current at location F3. A new interface appears. Click Established a connection to relay, which is to communicate with the relay hardware. A message like relay not found. Please check the connection. If you see this message, it means the system is unable to detect the relay hardware. This usually happens due to one of the following reasons. First of all, USB cable is not connected, or the reset pin on the relay kit not pressed. Ensure the USB cable is properly connected. Then press the reset pin on the hardware to initiate communication. Now I verify the USB connection, but the establish connection button is still inactive. It becomes active only after completing the proper sequence. Then first click on measure fault current and press on continue. Then press the reset pin again and again press on continue. Now the established a connection to the relay button is active. Click it and the message connection successful will appear. In the hardware setup, please connect the patch code from the fault switch to fault point F3 to create the fault condition at that location. Next, click the measured fault current button. After this, a message will be displayed showing the fault current during the fault at point F3. It shows around 6.82 ampere. Please click here to close to exit the message and then press the reset button to perform another test. Please repeat the experiment at any other desired fault point to measure the corresponding fault current. The experimentally measured fault current at fault point F2, F3 and F5 are tabulated as shown here. To ensure proper relay operation, we already discussed that the pickup current should be greater than the maximum load current and less than 80% of the minimum fault current. Therefore, the selection criteria for the pickup current can be expressed as the pickup current should be in between the maximum load current and 80% of IFI, that is 2 ampere, and I peak should be in between 2 ampere and 3.2 ampere. The maximum load current is taken as 2 ampere here based on the system 100 ohm resistive load. Based on this range, the value of I peak is chosen as 3 ampere to confirm the reliable operation of the relay. The other relay settings is to be found out as the time multiplier setting TMS and the multiplier of the instantaneous setting. The fault current at IF3 is required to calculate the time multiplier setting TMS of the relay in order to achieve the tripping condition within 3 seconds as mentioned in the exercise. The calculation procedure is outlined below. The tripping time is given as 3 seconds and according to the IEEE moderate inverse curve, the relationship is shown here. This is the defined IEEE equation and which is equal to 3 seconds. The only unknown in this equation is TMS, time multiplier second. Using this equation, the appropriate values of TMS is calculated as 0.93. For instantaneous tripping, for a fault at F2, the multiple of the pickup current is designated as N. Must satisfy the following condition. That is, the N should be less than the ratio of the fault current IF2 to the pickup current, or N is taken as 90% of this ratio. And from this, the value of the multiplier N is calculated as 4. Therefore, the expected shape of the relay characteristics of this particular problem is look like this. At F3, the relay should trip at around 3 seconds. And if the fault current is greater than N into pickup, the relay will trip the breaker instantaneously. From the main interface, begin your experiment by selecting Numerical Overcurrent Relay Experiment. A dedicated graphical interface for the relay experiment is now displayed. Click on Establish a connection to relay to initialize the communication with the hardware. A connection successful message is appeared. Please proceed to enter the pre-calculated relay settings to configure your protection scheme. The settings are already calculated. The pickup value for this particular exercise is 3 ampere. Relay characteristics is IEEE moderate inverse curve. IEC and IEEE curves are available, but in this problem, we use this curve, and the time multiplier setting of this particular problem is 0.93, and the instantaneous protection is enabled by just clicking on this checkbox, and we calculated the multiplier of the instantaneous setting is 4. So that will have a look on this characteristic equation at the top. If you want to find the formula for this particular characteristic equation, at the top there is a button like click here to open relay characteristic equation file. You can check the different relay characteristics and their equations and constant for both IEEE and IEC overcurrent relay characteristics. Coming back to the GUI, and here after entering all the settings, please click on the update settings to the relay. Now in the relay kit, the circuit is in active condition. All the LEDs are turned on now, and in the status of this GUI, the R1 breaker is turned on and fault switch is still in off condition because we didn't create any fault till now. Here the GUI offers an interactive relay characteristics curve for detailed analysis and engagement. If we click on the cursor on window, the feature to interact with the curve and simply hover to read the precise time and the current value from the graph. And if you want to zoom on, just click on this button and just zoom on the relay characteristic. In this case, we already know that for a current of around 6.82 ampere for a fault at F3, the relay will trip at 3 seconds. We can verify this by click on here around 6.8. The relay tripping time is around 3.01 second. Cursor off and zoom off, reset the view of this graph. Now please click on plot waveform. The real-time waveform of both the current and the trip signals are visible from this graph. Trigger a fault using the fault insertion button. The current spike instantaneously and the relay operate within around 3 seconds, that is 3.02 seconds. Because the current calculated is 6.82, but now due to certain voltage variation, the fault current magnitude is 6.78 ampere instead of 6.82 ampere. That is why the tripping time is not 3, it is 3.02 seconds. And verified it expected behavior. Use here, please click here to close this message and use this zoom on button to enlarge both the waveforms simultaneously like this, allowing precise time aligned analysis of fault current and relay tripping response. Click generate a report to automatically document the result. Save it on anywhere in your system. PDF saved successfully. You can open this waveform with the relay settings, result, characteristics curve, current and trips signal carrier. Click reset relay to prepare the system for the next test. This clear previous data and the result and reset the relay and breaker to the default conditions. Now insert a fault at F2 and confirm the operation of the instantaneous protection mechanism of this numerical overcurrent relay.